Continuing with counting, let's look at two things we're going to have to do count again and again. So let's do it once and figure out how to do it. So the first thing we're going to end up having to count again and again is where, suppose we have a bag with n things in it, n different things in it, and we draw k from the bag. Well, how many different ways can we draw k things out of n? Taking account of the ordering. So we're drawing k items out of n. How many ordered ways, where we care about the ordering, how many different sequences are there? And that's the permutations. And then the second case is where we don't care about the ordering. So that's a combination. And it turns out the product rule already gives us enough to do these calculations. So here's an example. Suppose we have a pizza. We've got 6 possible toppings. We have to choose 4 of those for a pizza. How many different pizzas can we make? Or suppose we have lottery numbers. We can choose 6 numbers between 1 and 47. How many different lottery numbers can we choose? And so on, right? That's the kind of things we're trying to count. So in a permutation, we care about the ordering. So for example, suppose we've got the letters A, B, C. How many ways can we arrange them? So we can have, so this is the set of ways, A, B, C, B, A, C, and so on. And we're going to count all of those differently because the ordering matters. So how many ways can we order A, B, C? Well, this product rule sorts it for us, right? So the first letter, we've got 3 to choose from. So there's 3 possible first letters. Then when we go to pick the second letter, there's only 2 left now. So there's 2 ways we can pick that. And when we go to pick the third letter, there's just 1 left. So the product rule tells us that there are 3 ways to choose the first letter, 2 ways to choose the second, 1 way to choose the last one. So we multiply them up to get the number of permutations, which is 6 in this case. And because this counting down thing, 3, 2, 1, so on, occurs a lot, it's got a special notation. It's n factorial, n with an exclamation mark. So we start with n minus 1, n minus 2, multiply them all up all the way down to n minus 1. That's what n factorial is. So 3 factorial is 3 times 2 times 1, which is 6. You get big numbers out of factorials quite quickly if you go try it on your calculator. So in general, if we have n objects, the number of permutations is n factorial, and that just comes straight from the product rule. So the number of permutations can be enormous very quickly. So here's the first wrinkle on that. Suppose we've got a word like moo. So to start with, let's treat the 2 O's different. So I'll put a subscript 1 and 2 on them, O1 and O2. Then we've got 3 letters, so we've got 6 ways of doing it, right? So we could have M with O1, O2, M with O2, O1, right? So we flip the order of the O's and so on. But now suppose, right, it's very artificial to have to tag the O's with a 1 and a 2 to distinguish them. Generally, we don't care. Moo is just moo. We don't care about the order of the O's. So if we're doing counting in that setting where we're going to treat some of the objects as all being the same, so then we collapse those 2 moos together, these 2 ones, and the ums together, and these are the set of arrangements. We've got moo, mo, and So how do we do counting when that happens? So we'll have a look at the repeated object. So that's the O's. There's 2 O's. How many ways could we choose the O's? Well, we know from our product rule that there's 2 factorial ways, which is just 2 ways of choosing the 2 O's from 2. And so what we need to do is take the total number, our 3 factorial, our 6, and then divide through by the number. Then we're going to group these together, right? So we're going to group those 2 together, those 2 together. And the reason it's 2 is because it's 2 factorial is the number of ways we can write the 2 different O's, right? So we take our 6, divide through by 2 to do with that, capture that kind of clumping together, and we end up with 3. So 6. So 3 factorial divided by 2 factorial, which is 6 divided by 2, gives us 3 permutations when we've got these. When we don't care about the O's, we treat them as the same. And that dividing through trick is a big one. That's an important one. It's very straightforward, of course, but it lets us do all sorts of things. So just to get that straight, this is an important one. Let's consider another example. So we have pepper. So now we've got 3 P's, 2 E's and 1 R. Let's label the P's with subscripts 1, 2, 3, so we can distinguish them, and the E's with E1 and E2. So if we take one arrangement, there's now too many to easily write out, but let's take one of them, the pepper. We put 2 P's at the start. How many ways could we write that? Well, we could write it as P1, P2, P3 like this, and E1, E2. We could then rearrange the P's in these different ways. And then for each of those, we could flip the E's around. So of course we can only enumerate one of these. How can we actually calculate it? Already it's getting quite hard just to enumerate things. We have to be a bit smarter and use our what we know from the product rule and this dividing through trick to do the calculation. So we know that this is 6 letters, so there's 6 factorial ways that we can rearrange all these P's and E's and R's, treating them all as individuals. If we have a look at the P's, there's 3 P's, so there's 3 factorial different ways of arranging the 3 P's. There's 2 E's, 2 factorial ways of arranging them, and the R, if we want this to be consistent, there's 1 factorial, there's 1 way of arranging the R's. So that means there's 3 factorial ways of arranging the P's, 2 factorial ways of arranging the E's. We multiply them by the product rule, so there's 12 ways to write out pepper. If you get them up, there's 12 of these. 6 factorial ways to write out all of these guys altogether. So we end up with 6 factorial over 3 factorial, 2 factorial, 1. That gives us 60 possible arrangements when we don't care about the order of the P's or the E's. Right, so already we're doing quite sophisticated stuff beyond what we could do by enumerating, but just using very simple ideas. And so here's the general setup. If we've got repeated distinct objects, so that's the P's and the E's inside pepper, or the O's inside moo, then what we do is we calculate the number of possible permutations of overall, so that's our n factorial. Suppose we've got, that's like in pepper, it's 6 factorial, n would be 6. And then we start dividing through by the number of groups, so P occurs in 1 times, E occurs in 2 times, so 2 twice, and down to R occurs 1. So this is the general setup for it. And in the special case when all the objects occur only once, there's only 1 P, there's only 1 E, there's only 1 R. All of these are 1, and we get back to n factorial, which is our original permutation rule. So it's a generalization of the permutation rule. So this is the end rule for remembering with permutations. The thing is, don't memorize this. Instead, remember how you got it so that you can actually do the calculations yourself and figure them out. It's best not to just memorize your way through these things, but to actually understand the ideas so that you can apply them. And you'll see later why that's going to be important.